gentlemen make an appearance. So I will be posting this in the content section of our D2L. It's Java coding style conventions. I'd like for you to follow something like this. It doesn't have to be exactly this. I'm not super picky, but if you look at this document, it's about 30 pages long. I'm not expecting you to go through it and do everything like it shows, because we don't know how to do most of what it shows. But at the very least, here's what I would like, is at the top of every Java file you write, include this information. Just put the name of the file, the author of the program, and what the class does. And right now we're writing programs with only one class, but pretty soon we may be writing programs with 2 or 3 or 4 classes, so each one could have a different description up at the top. And if you wanted to put what assignment this was, assignment 2 or whatever, you could do that as well. And also I'd like the date, but I didn't put that there. So put a header up here that indicates something about the project, specifically your name, what it does. And more than that's gravy. I'd also like the date and the assignment number. Then I'd like for you to document your variable names. If it's an incredibly trivial variable name like I, you're counting from 1 to 20, or what was our assignment, 2 to 30 or whatever, maybe not document it, but even then you could just say, this is the counter that will count to 30 or something like that. So go ahead and document your variable names. And it's true that if you pick your variable names good enough, it's possible that they are self-documenting. Right now I don't really know what first and last mean. Does that mean the first student, the last student? But if it said first name and last name, that's better. But still, it doesn't take you any time at all, just add a little comment. It makes your code look a lot more professional too. And if somebody else was helping you with the code, or I was looking at it grading, then be lots better. And when you go out and work in the real world, then people will expect you to document your code. So just this first page is enough for us to get on with it. Feel free to read the rest of this, or as much of it as you want. As we go on, I may mention more things, but right now that's enough. Put a good header in there, document your variables. I will put that on our content section right now. So when we last left off, I guess we were around here. How to define a constant. You define a constant with the final keyword. Now we're talking about inline constants, literals. These literals are called constants even though they have slightly different meaning. If I was going to create a constant for the variable pi, I would put final double pi is equal to 3.14 whatever. And I would not capitalize the word final. Thanks. That is defining a constant. However, these numbers that are hard-coded into it are called literals. They're also a constant of a sort. So for the next couple of pages, we're using that in that context. A constant is a fixed value. Here's some examples. Integer constants, 8, 45, 2 million. Floating point constants, 34.6, 0.009, 5 point, and specifically these are doubles. And the reason why is that Java assumes that any number you type that has a decimal in it is a floating point unless you put an F after it. Excuse me, it assumes it is a double unless you put an F after it. You put an F after it and then it says, oh, well, I guess that's a float. I could store that in a float, pretty cool. If you don't do that, it assumes it's a double and it won't fit into a float. So the default type for an integer constant is int, not long. So any number you type like that will store into either an int or a long. However, if you suffix it with an L, that turns it into a long that cannot be stored into an int without casting. Why would you do that? Well, if you type a number and then it actually winds up being larger than the maximum data size for an int, which is 2 billion as we've seen. So if we made this 3 billion, 6, 7, 8, 9, this actually would not compile, because that's larger than an int can be. And the default data type for int constants is integer, not longs. But we could say, no, that's really long. It's cool. Run with it. The default type for a floating point constant is double, not float. So it's kind of odd. They chose the smaller type as the default integer, and they chose the larger type as the default floating point type. And the only real consequence of that is that you should go ahead and just use doubles all the time. There's no reason to use floats. If you use floats, you wind up having to do dumb things like this. Float f is equal to 1.0f. You just have to put an f after every number you assign it. You can do that. There's nothing wrong with it, but you don't have to if you make it a double. That works just as fine. That works perfectly well. And a double is more precise. It's got, twice as many digits of precision, so the math is more accurate. There's no reason not to use it. So this code generates compilation errors. Where and why? Well, that line generates error because it leaves off the F. This line generates an error because it leaves off the F. Now why is that? Because we defined that as a float, not a double. But Java decided that all constants with a decimal point in them are doubles. So here we're trying to squeeze a double into a float. By adding the F, we say, no, that's not a double, it's really a float. So, possible solutions. Always use double variables unless you have a reason to otherwise, or you can force it to be a float with the F. They're using lowercase. I like uppercase, either's fine. I think the reason I started using uppercase is because when I do longs, that's a lowercase l. That's kind of lousy looking, Number is equal to, okay, that looks like 11, but it's not, it's 1L. There, that makes it a lot clearer. So I just decided to start capitalizing the F's along with it. So constants can be split into two categories. There are hard-coded constants, these literals that we've seen, that's a hard-coded constant, and named constants. Named constants are the variables that you define with the final keyword. Final double speed of light is equal to this. So this thing actually has two constants in this statement. That is the named constant, which we are defining and assigning a value to, and that is the literal constant, the hard-coded constant. Once a value has been assigned to a named constant, you cannot change it. The compiler will throw a fit. It won't let you. So if later on we decide that the speed of light is equal to 5, it just won't compile because it's already been declared and assigned and marked as final. So the reserved word final is a modifier. It modifies speed of light so that its value is fixed or final. All named constants use the final modifier. And it tells the compiler to generate an error. Standard coding conventions suggest that you capitalize all characters in a variable name if it's a constant and use underscores. That's just a convention, but there's nothing wrong with it. It makes that leap right out at you. Oh, that's a constant. I just need to go and find out where it's defined. Oh, by the way, if you get your homework and you've only scored a 1 on it out of 100, it doesn't mean you're bad. It doesn't mean you failed. It just means that it did not meet the requirements for one of two reasons. One is that there had a compilation error. And if there's a compilation error, I can't grade it. I'm not going to fix your code in order to grade it. Or the other is that it didn't meet the requirements. Like if it was supposed to count from 2 to 20, 2 to 30 by even numbers, and instead it prints out all the odds. That's, it's great, but it's not the assignment. So what I do is I give you a 1 just to let you know, hey, this needs fixing. But then go ahead and fix it, and as long as you get it in promptly in a week or so, you'll still make a good grade. So don't stress about those 1s. It's just a strongly worded hint that it needs to be fixed. So there are two benefits of using named constants. It makes the code more understandable. And if a programmer needs to change the named constant's value, the change is easy. You just fix it once. So say in your code, you had been making a whole bunch of calculations based on E is equal to mc squared, where c is the speed of light, and you had hard-coded this constant in it. And then your boss comes and tells you that he wants it to several more digits of precision. Well, you'd have to go and find everywhere in your code that you had defined that constant, you didn't make it a constant, you just use that, you copied and pasted over and over and over. You'd have to fix it everywhere that number occurred. Whereas if you define it as a constant, then you only have to fix it in one place. And I'll just repeat what I said. If you make a 1 on an assignment, it's because it either wouldn't compile or didn't meet the requirements. It's not a big deal. Just fix the assignment and then turn it back in, and you should get a good grade. So arithmetic operators. Plus, minus, multiply. And then there's division. Division's a little bit more complex. Addition, subtraction, and multiplication act exactly as what you would expect. If you print 3 plus 2, it's going to print 5. You print 3 minus 2, and it's going to print 1. If you print 3 times 2, it's going to print 6. And then lastly, if you print 3 divided by 2, well, what's it going to print? It's going to print a 1. Not going to print 1.5, it rounds it down. Why does it round it down? Because both operands are ints, and the division operator is finicky. If you give it a float on one side, then it'll do floating point division. But if you put ints on both sides, then it says, oh, okay. And the reason for that is because if you did this, int x is equal to 3 divided by 2, if this wasn't rounded down to be an int, then this would give you an error. It would be 1.5, which would not fit into an x. So integer division always produces an int, and the way it produces an int is by rounding the answer down. So 3 divided by 4 is 0. 99.999 divided by that is 0. If you want to make it do floating point math, you just make sure that one of the operands is a floating point. That's real easy. Just do this. There we go. Now it's 1.5. Let's go and put our answers back up here. So that's a 5. That's a 1. That's a 6. This is a 1, not a 1.5, because rounds down. And why does it round down? Because both sides are ints. If both operands are ints, then the division is integer division, which gives you an int as a result, which is rounded down. If there's no fractional component, it's fine. You know, if you printed 4 divided by 2, no biggie. It behaves exactly what you were expecting, because there wasn't anything left over. If you're curious about the remainder, like if you do this and it rounded it down, you can get the remainder using modulus. Percent is modulus. Modulus means remainder. So if you do print 9 divided by 5, that's equal to 1, because they're both integers, so it rounds it down. 5 goes into 9 one time with a remainder of 4. So if you print 9 modulus 5, that's 4, because there was a remainder of 4. Some languages have two different symbols, one that does floating point division and one that does integer division. Python, for example, will use 1 slash for floating point division and 2 slashes for integer division. But Java just makes it conditional on the operands. So let's do some math here. What is that as opposed to that? What is 10 divided by 3 when they're both ints? Oops. That is correct. And what's 10 modulus 3? It's the remainder. 3 goes into 10 3 times with a remainder of 1. Yeah. How about 10 divided by 5? What is that? Not a trick question. So what is 10 modulus 5? Well, 5 goes into 10 2 times with a remainder of 0. So that's why for that code where you were counting by even numbers, you could do this. counter is equal to 2 while counter is less than equal to 30. If you didn't want to add 2 to it each time, if you just wanted to add 1 to it each time, which is legit, you could do that. You just check to see if it's evenly divisible by 2. You check to see if the modulus of 2 is equal to 0, because if it is, it's an even number. So if the counter modulus by 2 is equal to 0, you know it's an even number. Have I done the dollars and cents example in here already? Okay, good. Well, how would you check to see if something was evenly divisible by 100? If you had 500 pennies and you wanted to know if that was exactly $5, how would you do that? Instead of modulusing it by 2, you could modulus it by, well, if you modulus it by 5, you'd make sure that there was only nickels in it.
Oh, that's true.
Yeah, so you could do it by 100. So x modulus 100, if x modulus 100 is equal to 0, you know it's a multiple of 100.
Oh.
If x modulus 1000 is equal to 0, you know it's a multiple of 1000.
That makes sense.
So say you have a variable called pennies, and your pennies is 456, and you want to know how many dollars that is. Let's just call this cents. You want to know how many dollars that is, and you want to know how many cents that is. To get the dollars, you could divide the cents by 100. 456 divided by 100, rounded down, is 4. So dollars is equal to cents divided by 100. That should have been pennies, excuse me. Then, what's left? Pennies is equal to, what's the remainder going to be? How do we calculate the remainder? Cents modulus 100. And then we could print out that this was dollars plus dollars and plus cents, like that. Hope that makes sense.
Yeah.
You could write a little program, this might be fun, I don't know, that would take an amount of money and then count the change. Count how many dollars, count how many quarters, how many dimes, how many nickels, and so on. Let's do that. Go to NetBeans. New project. I'm just going to call this one coins. No, I'm not going to call it coins there. I always do that. You choose Java application and then you get a chance to name it. Coins with a capital C. I'm going to clean mine up a little bit, but I'm going to leave this comment block here as a reminder, okay, that the author is my name here, and the description of the program is given a number of cents, this program determines how many dollars, quarters, dimes, nickels, and pennies make up that value. So firstly, let's ask the user for how many cents there are. So we're going to have to import. import java.util.scanner with a capital S. It's popping up a warning message saying unused import. Well, yeah, no kidding. We just haven't used it yet. Scanner in is equal to new scanner parentheses system.in. Now we can print. We can ask them how much. System.out.println. How many cents to convert? And int x is equal to, no, let's give it a good variable name. Int cents. Cents is equal to in.nextInt. Hopefully we aren't getting fractional cents. You know, if somebody took wire cutters and cut their pennies in half, I guess we could, but so it's a cleaner programming style if we put all of our variables up at the top of the function. So I'm going to move that cents declaration up there. And we're going to need more variables. We're going to need variables for dollars and for dimes and nickels and pennies and quarters. Let's just do a couple of those. And then I'll leave it as a exercise for you to fix it to do the rest. So int dollars, quarters, dimes, nickels. I always spell that wrong. And pennies. It would be nice if they were all initialized to 0, perhaps. So dollars is equal to quarters, is equal to, this is a cheesy way of initializing them all, is equal to dimes, is equal to nickels, is equal to pennies, is equal to 0. That gets them all at once. Alright, so the ones I'm going to implement will be, I'll do dollars, just going to put an asterisk above it. I'm going to do dimes, and I'm going to do pennies. And then I will ask y'all to spend a few minutes modifying it to do the rest as well. Okay, so first let's calculate the number of dollars. The number of dollars is equal to the cents divided by 100. And now we have to reduce the cents to the modulus of that value. And if you think about it, why is that? Because if it's $5.50, then we want the dollars to equal 5, but we want the leftover to be what was left. So we're modulusing it by the same amount. And that takes care of the dollars. Now we're going to do the dimes. I'm skipping quarters. Dimes is equal to cents divided by 10, and then our leftover cents is equal to cents modulus 10. And then lastly, pennies, it's just whatever's left over. There's no modulusing necessary to do pennies. Then we need some print statements. Now don't do what I'm about to type, but we could have done this. Pennies is equal to cents divided by 1. Cents is equal to cents modulus 1. That would be silly. The reason it would be silly is because pennies, this would give us the answer. What is something divided by 1? It's just always that number.
Yeah.
So that's silly. And if you modulus anything by something, it's 0. So we don't really need to do that. Assuming that we're done. I guess we could tack on cents is equal to 0 at the end just to indicate that we've done all of the money. Okay, it's possible this will even work. I'm not totally confident, but I will find out soon. And in case you don't remember, dollars are 100 pennies, 100 cents, quarters are 25, dimes are 10, nickels are 5, and pennies are 1. And the ones we implemented here are the dollars, and the dimes, and the pennies. How many cents to convert? 592 cents, which is $5, 9 dimes, and 0 pennies. I done something wrong. Oh, because I printed out cents here rather than pennies. Change that last line to actually print out pennies in both places. And if I hadn't have been clever and added that last statement, it would have worked. $641. $6, 4 dimes, and 1 penny. All right, if anybody needs a printout of this, I can print it out for you. Otherwise, get it working and then add code that'll calculate and print out the number of quarters and the number of nickels as well. And you just kind of need to pick the right place to put those in. And I can give you a hint after a little bit if you're stuck. Anybody getting compilation errors? All right, we have to add import scanner up at the top. There's 2 ways to do that. One is just to click on it, and I hate teaching people this because then they think they can fix anything by clicking over here and choose add import for java.util.scanner. So we have to add that at the top of all of our programs. How many points to convert? 698. Okay, go. You just need a semicolon after that one. Oh, where are we? Close whatever we just opened. Just need a semicolon after that. And we need a semicolon after that. We need a variable. We need to actually declare this variable, so make it int space cents. There you go. So I know some of y'all have done this already. Where am I going to put the calculation for the quarters? Yeah, because if I don't do it before I start counting dimes, then I'm going to have lost my chance. So I'll just put quarters is equal to quarter, the same kind of thing, cents divided by 25. And then the cents is equal to the cents divided by, or modulus 10. Now there's a shortcut. Sometimes do not type what I'm about to do. But you could do this. Cents is equal to cents plus 10, or you can just type cents plus equal 10. That's the shortcut for doing the addition assignment thing. It's called a compound operator. So anytime you're taking a variable, you're modifying it some way, and then you're storing it back in itself, you can write it in a short way. So, not that I'm recommending you do it, but you could do this. Cents percent equal 100 there. And then you could say cents percent equal 10 there. And what that does is it moduluses our cents value and then stores it back in cents. That should have been a 25. But that looks weird, that percent equals, but it looks a lot clearer when you see plus equals and minus equals. Okay, so 999 cents. Oh, I forgot to print the number of quarters. After you calculate the number of quarters, you should print them out as well. So you just have to add a print statement down here to print them out. In some money systems, there are bits. Bits are 1/8 of a coin. So instead of being a quarter, they're half a quarter. They're equal to 12.5 cents. Thus the expression, I can't think of any expression that uses the word bits. But shaving a haircut 2 bits, that means shaving a haircut 1/4. Piece, pardon me?
That's a cheap haircut.
Yeah, sure is. Or pieces of 8, the Spanish, same idea. A piece of 8 is 1/8 of a doubloon or whatever the coin that was being used. Okay, so this one has dollars, quarters, dimes, and pennies done. It doesn't have nickels. I'm going to leave nickels up to y'all to do. You probably already have them done. If not, just kind of go ahead and finish it really quickly while we decide what we're going to lecture on next. Okay, so the book is silly and it calls integer math grade school division. Well, I don't know when I learned that 1 divided by 2 was equal to 0.5 rather than 0. Probably in grade school. So I ignored that term. It's just integer division because the result is an integer and it's rounded down if there's any remainder. All right, expression evaluation practice. Given these initializations, use Chapter 3's operator precedence table to evaluate the following expressions. Well, I don't remember their precedence table. I'm sure it's in the book, but you can remember it real easily. It's PEMDAS. If you want to get technical about it, it's PMMDAS. P just stands for parentheses. Parentheses are evaluated first, or they change the order of the evaluation. MMD stands for multiplication, modulus, and division. Those are all done second. And then lastly, addition and subtraction are done. So you pronounce it PEMDAS. In some languages, there is an exponent indicator, either star star or the up caret symbol, the shift 6. Java doesn't have it, but pronounce the same, PEMDAS. Parentheses first, then multiplication and division are the same precedence, so you just do those left to right. And then lastly, addition and subtraction. So we have this expression down here. And we have more than one expression. But we have no pins. Ooh, the dirty rat who stole my pins. Okay, we won't write on the board. I've been told by some of the people who evaluate teaching methods, you shouldn't write on the board because as soon as you turn your back to the class, they'll start playing Candy Crush. But I find that when the teacher writes on the board, it can actually focus attention to it. Okay, so anyways, if z is a double and x and y are ints and x is equal to 10 and y is equal to 4, let's evaluate this. So what's the very first thing we're going to do according to PEMDAS? We're going to do all the stuff in the parentheses. So we're going to treat this as a separate expression. So we have an addition here and we have a division here. Which of those is going to get done first? Multiplication and division get done before addition and subtraction. So we will do this first. Now we have to decide, is this integer math or is it floating point math? Now you tell me based on the information up at the top of the slide. Are we all in agreement? Yeah, because these are both integers. So x divided by y. Well, x is 10, y is 4. What is 10 divided by 4, producing an integer? 2. Okay. I'm going to replace that with a 2. Now we can do the plus. So 6.0 plus 2. We're adding a double to an int, so the answer is going to be a double. 6.0 increased by 2 is 8.0. Now we can come over here and we check again. Are there any more parentheses? No. It's all just multiplication and division, so we just do that left to right. 8.8 divided by 10. Did I do something wrong? 8.0. Thanks. 8.0 divided by 10 is 0.8 times 2 is 1.6. So after we were done with that, the answer would be 1.6. Let's do the next one. This next one is absurd because it starts with 0 and then we modulus it, but we'll run with it. What is 0 modulus 10? Well, if you divide, yeah, it's just going to be 0. Okay, so that's 0, and that was inside of parentheses. That's why I jumped to it first. I didn't even ask you. What's the next thing we're going to do? Yeah, 0 divided by x. Well, we would if we were dividing by 0. Okay, so divide by x, that's still going to be a 0. And now we don't have any multiplication or division, so we just run left to right. And so the answer is whatever z was, which is 6.0. That one was a little bit silly. Increment and decrement operators. If you have the phrase, the expression x is equal to x plus 1, you could word it like I showed you a minute ago, x plus equals 1. That is correct, but there's an even shorter way to express it, which is just x plus plus. And now you get the idea of where the C++ language got its name from. It's a better version of C. And x is equal to x minus 1, you can express as x minus minus. This is called incrementing and decrementing. That's the increment operator. It increments it by 1 and it increases it. So if you increase something, can you decrease it? Decrease. Yeah, I guess so. For a minute I was thinking I was making a funny joke, but it's not. It's just true. It's just pronounced differently. We would have to call it the decrement operator. Proper style dictates that increment and decrement operators should be used instead of statements like this. So when I'm first showing code, I will show things like that because it's crystal clear what it's doing, hopefully. But then very quickly, we introduce that, and then we just stick with that from here on. And these are the compound assignment operators that I showed you. X is equal to x plus 3 can be replaced by x plus equals 3. X equals x minus 4 can be replaced with x minus equals 4. Just takes the value of x, adds 3 to it, stores it back into x. And there are several of them: addition, subtraction, multiplication, division, and modulus. Tracing practice. Trace this code fragment. Well, I'd be more interested in doing it if I had my pen. Let's go ahead and do it. A is equal to 4 and B is equal to 6. If we were going to write this in the long form expression, it would be what? A is equal to A minus what?
Minus 6.
Yeah, minus B, minus 6. So what is A equal to after this is done? Yeah, because 4 minus 6 is negative 2. So right now, A is equal to negative 2. And now, B gets decremented. B was 6. What is it now? 5. And then C gets incremented. You can increment regardless of whether it's a double or an int. So C was 2. And now it is 3.
Or 3.0, I guess.
Yeah, 3.0. Let's be precise. And then C times equals B. Well, that means what? C is equal to C times B. Well, C was equal to 3. B is equal to 5. So if C is equal to C times B, then what is C now? That's equal to 15.0.
Yeah.
And then lastly, we'd print out A plus B plus C, whatever. Minus 2 plus 5 plus 15. 18, yeah. I more care about this stuff than throwing in one last random expression at the very end. Typecasting. Typecasting is when Leonard Nimoy plays Spock for the rest of his life and can't get another job. Typecasting is when you convert a data from a larger format to a smaller format. That's called demotion. Promotion is when you take a smaller format and you store it in a larger format. You can promote an int to a long easily. You don't have to use any special syntax. But if change is a long and it needs to be stored in an int, then you force it that conversion with the type, which is the parentheses followed by the data type. So to go from a long to an int, you have to type it. In order to go from a double, which is a large format, to a float, you have to type it. To go from any floating point type to a non-floating point type, you have to type it. That sounds... Why am I saying type? Repeat everything I just said except throwing the word cast in liberally. This is called casting. They threw me off with the word type up there. This is called casting. So if we have an I here, have I already lectured about this? Is this going to be belaboring the point? Okay. So we have an integer, we have a long, we have a float, we have a double, this is totally legal. L is equal to I. It is no problem to store an integer into a long. Ta-da, this is great. I is equal to L, that's an error. It will not compile because a long is 64 bits wide and int is 32. The compiler is worried that we may suffer data loss, so it will not allow that to happen. Won't compile due to possible data loss or precision or whatever the specific error message is the compiler gives us. But we can fix it with a cast. We can say take that L and cast it, just like pouring iron into a mold to reshape it, into the form of an int. Okay, it will work now. However, there is some risk there. If L is too large to fit into an int, then we have a problem. Let's do that up at the top of our program just for giggles. Int I long L is equal to, and we're going to make it larger than will fit into an int, so I'm going to make it equal to 40 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. This will not compile because this number is too large to be an integer. The default type for hard-coded literals is int, but I can fix that by adding a L.
Yeah.
Okay. And now I want to store that L back into my int. And he says, no way, Jose. Incompatible types, possible lossy conversion. But we will go ahead and say, hey, compiler, I'm smarter than you. It's okay. And then we do it. And then when we print out the value of I, system.out.println I, we will find that it does not print 40 billion. Instead, it printed 13 billion or some number like that. So the data was corrupted because it was too large to fit into an int. And that's just the risk you run whenever you cast. When you cast, you're telling the compiler, I know best, and I'm pretty sure that that number will fit into the range of an int. Because what's it supposed to do? The compiler doesn't know ahead of time this value. We could be prompting for this value. So it's not like it can go, oh, it's okay to cast this number, but it's not okay to cast that number. If you were really, really worried, you could do a check first. You could do if L is greater than integer.max value, then go ahead and do the conversion, else print an error message. That would be about the best you could do. Won't fit into an int. We could even print out the number first. But usually when you see people casting, they don't go to all this effort. They just have a reasonable assumption that the data is acceptable in an acceptable format already. Oh, now look at that. Oh, it should be less than or equal to, not greater than. I had my logic wrong. Because what is the error state? The error state is if long is actually larger than integer. So I should swap these things. So I will say if L is less than or equal to the maximum value, then do the cast, otherwise print the error message. And then it says, okay, 40 billion won't fit into an int. You can also use casts to go from floating point types to ints. If I do this, int I is equal to 3.0, well, even though it's a 0.0, it's still not an int because these are stored in different formats inside the computer. This is stored as a floating point type, which has a very defined type, which includes your mantis and your exponent, and there's no way that that can be stored into an int. Also, floats and longs, floats and doubles can hold astronomically larger values than ints. A float can hold a number with at least 30 zeros, it may be 38 or 34, I forget which, and a double can hold a number that's followed by 308 zeros. There's no way you could fit that into an int. But you can force it. You can cast it. Now when this is done, I is equal to 3. I is still equal to 3. It just truncates it, right. So we could do the same thing. Double D is equal to 9.999999999, whatever. And then I is equal to the integer version of that. I is now equal to 9. I'm trying to remember if modulus only works with integers. I think that Java used to be written that way, but I believe now you can also do modulus with floating point types. Let's find out. Which is an odd idea, but if we have the number 3.2 and we want to modulus it by 1.6, that should be 0. Because 1.6 goes into 3.2 2 times with no remainder. That used to be a compilation error, but it actually worked now. So that leaves C and C++ as one of the few languages where you cannot use modulus on non-integer data types. We are still recording, are we not? Good. Sometimes you need to use casting or you can use casting in order to force a calculation to be correct. And I'll give you an example. If I want to calculate pi, the formula for pi looks something like this. 1 minus 1 divided by 3 plus 1 divided by 5 minus 1 divided by 7, and so on out to infinity. That is the formula for calculating pi. There may be faster formulas for calculating it, but that is the canonical traditional way of doing it. Now when I print this out, it's not going to print out 3.14159. It's not going to print out anything even close to that. What's it going to print? It will print 4, or 4.0. Why did that give us 4? Well, what's 1? That's 1. Now what is 1 divided by 3? These are integers now. So it's 0. And what's 1 divided by 5? 0. And what's 1 divided by 7? 0. So that is pretty easy to fix. We just have to change one or the other to floating point data types, like that. Now it would actually calculate correctly. It's still not very precise, but at least it won't be 4. It gets more and more precise the more terms you add to the equation. Right now it thinks pi is equal to 2.8, but if I added some more, plus 1.0 divided by 9, then it'll be a little bit better. Go away. Where'd my output go? Oh, it's right down here. There we go. Yeah. So it keeps oscillating, getting closer and closer and closer to our favorite value, 3.14159. And it takes actually quite a while for it to get that precise. You can code this in the form of a formula. Whenever you see a series of numbers like that, you can look at it and think to yourself, well, I'm a programmer. I could code that into a loop, and it would run, a certain number of times, or it would run until a certain precision had been calculated. We're not going to do that now. The point of that was to show that the calculations can mess you up, and even if the math looks perfectly good, like that, then it doesn't work. But you can also use casting to fix that. Like, what if we had some counter x here, and we were going to use that over and over and over? Well, one way to fix that would be that, but another would be to say, okay, this is really a floating point. There is no such thing as x. Let me give that a value. Yeah. We've gone far afield from this actually being a valid calculation of pi. But if we needed to take x and have it divided into 1, and they were both integers, but we wanted to allow floating point answers, this is one way we could do it. We would cast the numerator, the denominator, as a floating point, so that these both were not integers. Otherwise, this would be doing integer math and we would get something wrong. Or you could do the same thing up on the top. Cast that. The easiest solution, of course, would be to do that. Okay, int y is equal to 4, and then double z is equal to x divided by y. We need a way to get this to actually do valid math, so that 3 divided by 4 would be 0.75 rather than 0. We could put the cast in 2 different places. We could cast the denominator, or we could cast the numerator. This won't work. How about if we do this? Or double. That will work. Except now I can't. Yeah. Or cast the top part. Z is equal to double x divided by y. I want to make absolutely sure that will work, so I'm going to print that out. Because part of me wants to put parentheses around this expression here, like that, to make sure that that gets done before we start dividing anything. Alrighty, it equaled 0. This is not a valid way of doing it. What would I do to fix that? I think I already showed y'all, but if you weren't watching, think it through. I want this x to be converted to be a double before the division occurs. Because right now the division is happening first, kind of like PEMDAS. Multiplication and division happen before anything else. It also happens before casting. So I can force it with parentheses. That says do this conversion first and then divide the results by y. And now when we run it, it'll actually equal 0.75. Or will it?
It worked for me.
Oh, here it is up here. Was I looking at the wrong one? Did it work the first time too and I just didn't notice? Let's find out. I was fooled by that one. I don't know where that print statement is. Yeah, it did work. Okay. So casting is an even higher priority than PEMDAS. Good to know. So if we were going to put a new precedence list, then we will put casting up at the top, and then we will put parentheses, and then multiply, divide, and modulus as a third tier, and then addition and subtraction. So I guess you could call it CPEMDAS. I don't know. Just remember that order. Then you start wondering whether plus plus happens before or after the math is done. There are two forms of the plus plus operator. It can precede the value and it can follow the value. And what do I mean by that? If I set x is equal to 1 and then I do system.out.println x equals, and then I do x plus plus, is x going to be 1 or 2 when it prints out? You may be tempted to say 2, but it's going to print 1. And then after it's done printing, x will equal 2. And the reason for that is if you follow the variable with the 2 plus signs, that means do the entire thing and then only increment after everything, absolutely everything else is done. So after that expression runs, after that print statement runs, it will print 1 and x will then equal 2. But if you do this, now that looks really weird because it's got multiple pluses. Sorry about that. But you get the idea. It will print out 2 and x will equal 2. And the reason why is if you precede, if you use plus plus as a prefix rather than a suffix, it's the very first thing that happens when execution of that line begins. So if you see plus plus in front of the variable, that means that when it hits that line, that's the very first thing that happens. And so x was 1, but whoops, lickety split, it changes to a 2, and then we print it out. So it will print 2 and x will equal 2. Just remember, x plus plus, the suffix means that it's done after everything's executed, kind of like after the semicolon. You could rewrite this like this. If you had this statement here, this would be the same as wording it like this. Does that make sense? All this gets done first, and then the incrementing happens. Alrighty. I may be lectured out. Yeah. Let's stop here. Let's create a Dropbox for our dollars and cents program. And then we will meet again on Thursday. And I'm really curious as to where the recording will be synced up or not, so I'll find that out pretty quick.